The story of the sun starts 13 billion years ago with the Big Bang. In an instant, the universe was born, and since then, it's been expanding at the speed of light. Within the universe, there are 100 billion galaxies. Our galaxy is but one of them. In it, there are 100 billion stars. And towards the outer edge of one of the spiral arms is an almost insignificant dot. A medium-sized, not very bright, undistinguished star. Up close, it's a different story. On the planets closest to the Sun, Mercury and Venus, the heat is intense, their surface is scorched. Further out through the solar system, the Sun's rays weaken until they are powerless against the chill of space. The outer planets are frozen. But in the middle lies the Goldilocks planet. Not too hot and not too cold. In fact, it's just right. And life has flourished in the warm glow. All life on Earth owes its existence to the sun. It powers every natural system and sustains every plant and animal. Without the sun, the planet would be a barren, lifeless ball of rock. Recognizing that power, humans have always worshipped the sun. But we have also always striven to understand it. These monuments are more than just temples. They are calendars and observatories, tools for studying the sun. And some of them are still operational. This is Orkney. To live here is to know the importance of the sun. In the summer, the days are long and full of light. In December, it's a different story.
It's a midwinter. It's about 11 o'clock in the morning. It's still not light completely. There's a strong wind coming in off the Atlantic, and it's cold and it's wet. And that's pretty much typical of this time of the year up here.
Yet despite the cold, in the Stone Age, 5,000 years ago, a civilization thrived here. The island is covered in the remains of their society. The ruins are full of mystery. We know little about the people who lived here. But they did leave evidence of the important role the sun played in their lives. Maes Howe, 1,000 years older than the pyramids, is one of the finest examples of Stone Age architecture.
Well, entering Maes Howe, you have to crouch right down, and they're confronted with a passage which seems to actually go on and on and on. Slightly feel an impression of going uphill, up slope, and coming through clearly another doorway. Suddenly, the whole thing opens out into the most amazing chamber. This alone is probably the highest and largest enclosed space that Neolithic Orcadians would have experienced. When it was excavated, when it was first entered back in the 19th century, the clay floor was littered with broken pieces of human skull. This is a place of the dead. This is a house of the dead.
Most of the time, the occupants of the tomb were left in complete darkness. Then, at sunset on the winter solstice, the shortest day of the year, something amazing happens. The light of the setting sun shines straight up the entrance tunnel and illuminates the interior.
Well, the significance is that it's marking the shortest time of the year with the least light. And from that point on, slowly and gradually, the light is going to increase, the days are going to grow longer. So what's happening here is that the dead, the ancestors, are being awoken on that shortest day.
The winter solstice events at Maze Howe demonstrate an intimate and precise knowledge of the sun's movements through the sky. It was the first step on our journey to understand the sun and its many effects on us. To complete that journey, we've had to travel to the furthest depths of space and to the heart of the smallest atom. And with every closer look, the sun has always surprised us. To our ancestors, its power was its reliability, always on time, never changing. But the reality is proving to be very different.
Most people think of the sun as quite a boring, constant sort of thing, but in fact it's not at all. It's changing all the time, and if you look, you can see those changes on a matter of minutes or hours, and it's far from static and boring. It's changing, and it's got a life of its own.
Modern solar observatories magnify and filter the sun's light to get past the constant glare and give a clear view of the surface. This is the actual face of the sun. It is turbulent and boiling. Never the same from one second to the next, the surface bubbles like a giant bowl of porridge. Each bubble is 1,000 miles across. The heat and light brought to the surface raises its temperature to 6,000 degrees centigrade, enough to vaporize solid rock. And the sun is huge. You could fit the Earth inside it 1,000,000 times over. Periodically, huge explosions rip through the surface, releasing the energy of 1 billion atomic bombs in seconds. All this is on the surface. To understand the sun, we must know what is going on deep inside. That is where the power is generated. So for centuries, scientists have been devising ways to probe the heart of the sun. Some of them have been complex, and some of them very simple. And the first step is to figure out just how powerful the sun is.
It's easy to appreciate the power of the sun on a nice hot summer's day like here in the Texas Gulf Coast, and you can feel the power of the sun in your skin, sunscreen's on, but man, the sun is just, you know, the actual physics of what's going on inside the sun, the power that the sun, the energy that the sun is releasing is almost beyond comprehension.
But it is only almost beyond comprehension. And you can measure its power output with some simple apparatus.
One of the earliest experiments to try and measure the actual power of the sun was by astronomer William Herschel in the 19th century, where he had the brilliant idea of just watching a piece of ice melt to see how long it would take, and therefore from the properties of the ice work out how much sunlight was coming to the ground.
As a demonstration of the sun's power, it doesn't look that impressive. But Herschel realized that he could use the time it takes to melt one bit of ice to calculate the sun's total power output.
So here we see the ice is almost completely melted, roughly 29 minutes, almost half an hour, But Herschel was able to use this experiment and the time that it took to melt the ice to work out some basic properties of the sun.
Here's how Herschel's thinking worked. In the time it takes to melt a slab of ice on Earth, the sun is radiating heat in all directions, enough to melt a complete shell of ice around it, a diameter of 300 million kilometers. A shell half a centimeter thick and 300 million kilometers across contains a lot of ice, enough to make an ice cube bigger than the Earth. To melt that much ice in just 30 minutes would take an energy input of 1 billion watts. It's a rough but surprisingly accurate experiment. Modern satellite readings confirm the figures to within a few percent. It's an almost unimaginable amount of energy. If we could harness the sun's power output for a single second, it would satisfy the world's energy demands for the next 1,000,000 years. But it's one thing to know how much power the sun is producing. It's something else to know how it's doing it. Until the middle of the 20th century, no one had any idea what made the sun work. For scientists in Herschel's time, it was a mystery.
One of the issues was, of course, what powered the sun, and some very clever people actually considered the fact that the sun might be powered by burning coal. I mean, it seems ludicrous, but why not coal? That was an important source of energy on the Earth at that part of the 19th century.
If the sun was made entirely of coal, there would be one unfortunate consequence. It would burn itself out in just a few thousand years. Today that sounds ridiculous, but 200 years ago, it didn't seem so unlikely. It was widely believed that the Earth was only a few thousand years old. But in the mid-19th century, a new science was emerging that was painting a very different picture of the age of the Earth. By looking at the deepest layers of rocks, geologists were discovering that the Earth was much older than anyone had previously imagined. If that was true, then the sun also had to have been burning for much, much longer.
You can see the strata and the lines in the rock and background here that represent hundreds of million years of geological history. The top of Sacramento Peak, up beyond this, we find fossils that are 300 million years old. Below Sacramento Peak, we've got more than a kilometer of these strata that are far older than that. From the age of these strata, geologists knew that the Earth was at least 1 billion years old. At the same time, astronomers thought that the sun was only 10,000 years old. If the geologists were right, then astronomers had to find some other source for the sun producing its energy.
The search for the source of energy that could power the sun for billions of years lasted for nearly a century. Eventually, scientists would find the answer in the forces that hold atoms together and in the nature of matter itself. But first, you have to know what the sun is made of. To find that out, you need to take a very close look at sunlight.
When you take the light from the sun and pass it through a prism, spread it out into the colors, as you look through it, you notice that it isn't uniform, that there are places that are darker. Each of those dark lines is due to a specific chemical element. Each element has its own series of lines that are specific to it.
Each chemical element absorbs light at specific frequencies, removing a strip from the spectrum. As the light passes through the sun, all the elements leave their mark. So when the light arrives at the Earth, it contains the complete chemical formula of the sun.
If we take the spectrum and spread it out to fine details, and what we've done here is stack up pieces of the spectrum one on top of each other, you see all of these dark areas. The key to figuring out how much of these elements are there is the breadth and the depth of the line. How dark is the line and how broad is it?
The composition of the sun lies in this barcode. All the thin lines are caused by tiny amounts of complex elements, metals like iron and magnesium. But there are 3 very deep broad lines, and they are all caused by an enormous amount of a single element. There's some helium and traces of heavier elements, but over 90% of the sun is hydrogen. It's the simplest and most common element in the universe. The secrets of the sun's power must lie in this gas. Look carefully into the night sky, and you'll see huge clouds of hydrogen floating in interstellar space. These are nebulae, and they can be hundreds of light years across. They are some of the brightest areas in the sky, lit up by the intense light of newly formed massive stars. In them, we can see stars being born. It is to areas like this that astronomers turn their telescopes when they want to study how our sun was formed.
There she is. Okay. So now let's recenter on her.
By studying different nebulae, it's possible to piece together the stages in which stars are made. And it all starts in a cold, dark cloud, floating around waiting for something to happen.
Cold clouds like this are actually quite stable. They will sit there for a very, very long time, for thousands and in some cases millions of years before they'll actually do anything. What you need to do to get the star formation process going is you need to kick it with something. That can be an impact on the cloud from one side by a supernova blast wave. A massive star nearby has gone boom at the end of its life, and that sends out in all directions very energetic compression waves that hit the gas and compress it.
The shock waves knock the cloud out of balance, causing localized clumps of hydrogen to form. These are the seeds from which stars grow. The increased gravity of the seeds sucks in more and more hydrogen in a runaway process that lasts for 1 million years. As more hydrogen is squeezed into the clumps, the temperature rises. They are not yet producing light, but they are well on their way to becoming stars. As they grow bigger and bigger, they start to spin and throw out a disk of debris that will coalesce to form a solar system.
This kind of process is exactly the kind of process that would have formed our solar system. When we look at our solar system, all of the planets rotate around the sun in the same direction, and they all are in the same plane, the same flat sheet around our sun. And this is exactly a consequence of the fact that the early solar system formed out of a broad disk.
With the solar system in place, all that is left is for the young star to light up. When it happens, it is sudden and irreversible.
Ultimately, the process starts. And because it liberates so much energy with that first fusion, then the process takes off. It lights up a large area and it starts to shine on its own within a matter of minutes. It's a very quick process.
In that first burst of light, the star has begun its lifelong activity as a factory for making other chemical elements. Every atom in everything around us was made in the heart of a star, and all were made from the same starting ingredient.
The simplest element that we have is hydrogen, and it's actually the building block for all the other elements that we have.
In the heart of the sun, hydrogen nuclei, protons, are stuck together to make helium. It sounds straightforward, but it can only happen in the most extreme conditions.
In order for these protons to come together, because they're both positively charged, they don't want to come together. They've actually got to be pushed together. In order to do this, you need very high temperatures, so they're moving very fast, and you also need very, very high pressures.
The only part of the sun that is hot and dense enough is the core, an area that contains over half the star's mass in less than 2% of its volume. Here at 15 million degrees, the protons are bashed together so hard that they fuse. A helium nucleus is a tiny bit lighter than the combined mass of the 4 protons it is made from. And as Einstein tells us, it is that tiny bit of lost mass that provides the power.
Energy is equal to mass times the speed of light times the speed of light. Now, the speed of light is a very, very big number. So if we just take a small amount of mass, we get a huge amount of energy. And that's the energy which actually powers our sun.
Every second, 5 million tons of the sun is converted to pure energy. And although it has been burning for 5 billion years, it is only halfway through its supplies of hydrogen. The light produced in the core must travel over 500,000 kilometers to the surface, and it does so very slowly. The heart of the sun is so dense that the speed of light is less than 1 millimeter a second. It can take 200,000 years for the light to travel from the core to the surface. It takes just another 8 minutes to get to the Earth. This is what the power of nuclear fusion looks like from 150 million kilometers away. This is what it looks like close up. The H-bomb was man's first attempt at recreating the sun on Earth. A balloon full of hydrogen squeezed until it released its energy. In contrast to its destructive power, it's long been realized that controlled nuclear fusion could solve the world's energy problems. It has been one of the holy grails of science for half a century.
This kind of power, the H-bomb, is a man-made version of this, the sun. In 1958, Britain announced that she could produce this power in the laboratory in a machine called Zeta. There is a real prospect of unlimited energy from controlled thermonuclear fusion.
Unfortunately, it wasn't that easy. But now, nearly 50 years later, in the same laboratories in Oxfordshire, scientists are finally managing to create their own star on Earth.
NDI, ready when you are?
Okay, ready.
Prepare in shot 1, 4, 6, 5, 8. Starting shot in 5 seconds.
It might not seem like much, but slowed down by 300 times, the pictures reveal how the gas plasma is being squeezed and heated to create the most extreme conditions in the solar system.
Plasmas I always like to think of as being like naughty children. They're full of energy and they want to misbehave, and it's our job to try and control that misbehaviour.
For the particles to fuse on Earth, the temperatures need to be raised to 10 times those found at the heart of the Sun. Bombarding the gas with a stream of fast neutrons raises the temperature to over 100 million degrees. Only then can the energy of nuclear fusion be released. After years of learning to control the plasma, scientists now believe they are within sight of harnessing the Sun's power.
The aim of it is to be able to produce cheap, clean and effectively an inexhaustible supply of electricity for future generations.
This is only a small experimental reactor. It can only run for a few seconds and sucks up more energy than it creates. But the next generation of bigger reactors is already being built. When operational, they will produce 10 times more energy than they use. They will be stars on Earth, power stations that won't deplete natural resources or produce dangerous waste products. It sounds great, but recreating the Sun isn't easy, and it may be another 50 years before the fusion power station becomes reality. Until then, we'll just have to make do with the real thing. But that's not so bad. Just seeing sunlight is enough to cheer us up.
Well, many people think it's the warmth of the sun that is associated with us feeling good, and of course that's true. But in fact, research has shown that it's not really the warmth, it's actually the light that's important.
Sunlight controls our daily cycle, making sure we wake up in the morning and go to sleep at night. When there's not enough light, those patterns get disturbed with miserable effect. It's a clinical fact that depression is more common in winter because of the lack of sunlight. They call it SAD, Seasonal Affective Disorder.
Seasonal affective disorder is a depressive illness that starts during the autumn and early winter and usually goes away completely during the spring and early summer. Some people feel quite miserable and depressed and gloomy during the winter months, and some people, a small proportion, will go on to develop clinically significant depression, which requires treatment.
This is Rattenberg, a fairy tale Austrian village cursed by lack of sunlight. Due to a quirk of geology, it gets no sunlight at all between November and February. During those winter months, the sun never rises high enough to clear the brow of Rat Mountain. And the town lies in permanent shadow, while its neighbor across the river basks in the sunshine.
In winter, of course, it's very cold, it's shadow, and as you can imagine, it's cold, we are freezing, and if you want to have some sun, you have to move to the next village. It makes you happier to sit in the sunlight and not to freeze in the shadow.
Frozen and in the dark, the residents have been forced to take desperate measures to bring some light into their lives. Helmar Zangel is a lighting expert who specializes in bringing natural light into some of the world's biggest buildings. He may be the salvation of Rattenberg.
Evolutionary speaking, man has adapted to natural light and has adapted to the sun. And if we deprive man of the sun, clearly it's a different quality of life. How do you feel if you sit for 1 week in a place with fog? And how do you feel when you sit for 1 day in a place where the sun shines? I personally feel so much happier in sunshine, I can tell you that.
The solution for Rattenberg is simple. Steal some of the sunlight from the other side of the valley. Eventually, a huge system of mirrors will reflect the light of the sun to a second set of mirrors on the castle above the town, and then reflect it down into the streets to brighten the lives of the citizens of Rattenberg.
The main effect for the people in town will be that part of the facades of the buildings and parts of the street, at least of the main street, will be brightly illuminated and will clearly be recognized as sunlight.
It sounds crazy, but it's true. People will go to extraordinary lengths for a bit of sunlight. But the sun is much more than a giant light bulb. There are other forces at work in the sun. Forces that change over minutes and over years. Forces that tear the surface apart. We are only now beginning to understand these forces and the effects they have on the Earth. But we've known about them for hundreds of years, because the sun gets spots.
Sunspots are dark regions on the surface of the sun, typically about the size of the Earth in terms of area. Here's a live shot of one. Today, unfortunately, we've got a very windy day with high thin cloud. The picture is bouncing around and not very sharp, but with very high resolution images, we can see detailed structure in the sunspot. The inner part of the sunspot, the dark umbra as we call it, is dark only in comparison to the rest of the sun. It's actually bright enough that it would blind you if you looked at it alone.
The spots are not static. These video images show the edges crawling, almost as if it was alive. The movements of sunspots have been studied for 400 years, ever since Galileo trained his telescope on the sun and made the first crucial discovery about its behavior. Surprised to see black dots creeping over the surface, he kept track of them over a number of days and found that they were all moving in the same direction. To Galileo, the meaning was clear. The sun was rotating and was turning faster at the equator than at the poles. It was a discovery that was to prove critical in our understanding of how the sun works. Ever since Galileo, records have been kept of the coming and goings of sunspots, and variations soon became clear. Sometimes the sun is covered in hundreds of spots. Other times there are none at all. And after a while, a pattern emerged.
If you observe sunspots over several years, they come and go with about an 11-year cycle. From solar minimum, where there can be no spots at all on the sun for weeks or months at a time, to a maximum where you can have 100 spots visible on the surface of the sun, and then a decline again, usually over about 6 years or so, to back to minimum.
Until recently, no one knew what was driving the solar cycle, or where sunspots came from. But people had always suspected that the scars on the sun's surface had an effect on the Earth. But no one could quite put their finger on what it was.
It has been correlated with all kinds of different things. The price of wheat, the thickness of fur on animals. I'm inundated with it every day. I got a guy that comes to my website to try to predict the stock market from the daily sunspot areas. And he's like, oh, you didn't post them today. I got to know. So you making money or what? If I want some, if you are.
One effect sunspots do have on the Earth is on the climate. But it is a subtle effect. Its greatest impact was only noticed 300 years after the event. It was discovered in Greenwich by the astronomer Robert Maunder, who was studying the hundreds of years of sunspot records held at the Royal Observatory.
And in the late part of the 19th century, he became particularly interested in the sunspots. He discovered that there had been this peculiar effect in the second half of the 17th and the 18th centuries when the sunspot numbers diminished to really a fraction of what they are today. And he described this as the Maunder minimum.
For 70 years, from 1645 to 1715, sunspots disappeared. It was as if the engine that drives the solar cycle had stopped. And it correlated almost exactly with the last period of prolonged cold to strike the northern hemisphere. They call it the Little Ice Age.
What's interesting about a period like the Little Ice Age is that you don't necessarily see a very large dip in temperatures, but nonetheless, even a degree or two is enough to see some really quite dramatic effects, like pack ice advancing south from the North Pole, like the Viking colonies in Greenland being wiped out by the change in climate, and the population of Iceland falling by half. Now in Britain, the weather was cold enough that the Thames would regularly freeze in winter, and one of the classic depictions of life at the time is frost fairs, when the population would hold a fair on the frozen river. So things really must have been a lot harsher than they are today.
When the sunspots disappeared, something on the sun changed that cooled the Earth down. But it wasn't that the solar output changed. No matter how many sunspots there are, the sun doesn't get any hotter or brighter. So the spots must have another effect. And to see it, we need a different way to look at the sun. It's not just heat and light that the sun is throwing at the Earth. As every sunbather knows, there's ultraviolet light too. Enough UV reaches the surface to burn our skin, but it is only a fraction of the sun's UV output. The rest is filtered out by the atmosphere. It means we don't get a complete picture of the sun from the Earth. To see it in all its glory, you have to go into space. From here, you can really see the changing sun. In the extreme UV, the sunspots burn a brilliant white. In the X-ray frequencies, they look even more dramatic. Huge plumes of superheated gas spout from the spots.
When you're seeing the visible, you're really seeing the surface of the sun. But when you see the ultraviolet or the X-rays, you're actually seeing that very hot atmosphere, and that's about 1 million degrees, whereas the surface is about 6,000 degrees. So you're seeing a different part of the sun, and you're seeing a part that's constantly changing.
These phenomenal displays of solar power were only discovered in the 1970s by the astronauts on Skylab. No one had seen the sun like this before. Since then, a number of space telescopes have been deployed whose sole purpose is to look at the sun. The most used is SOHO, the Solar and Heliospheric Observatory. It sits 1 million miles away from the Earth, at the Lagrangian point, where the gravitational pull from the Earth and the sun is equal. Fixed in space, it has an uninterrupted view of the sun and its tantrums.
It has completely transformed our understanding. You can essentially see right from inside the sun right through to the coronal mass ejections as they're leaving the sun, so you're seeing way out to 30 solar radii.
SOHO has played a key role in understanding the explosive power of the sun. By blocking out the disk, it simulates an eclipse, revealing the outer atmosphere and the true scale of the sun's largest eruptions. These are solar flares and coronal mass ejections, and they erupt from the heart of sunspots.
The temperatures in a solar flare will be tens of millions of degrees. So it's an extremely hot, very dramatic change in temperature over a short period of time. When they erupt completely, you can get masses which are roughly the mass of Mount Everest being flung out into the solar system.
At solar minimum, flares are infrequent. But every 11 years when the cycle peaks, at solar max, the sun puts on the best firework display in the solar system. Solar astronomers are now beginning to understand the cause of these explosions. They are not caused by the power of fusion. There is another force at work. It is the force of magnetism. The sun is covered in a complex network of magnetic fields. A magnetic map shows a familiar patchwork on the face of the sun. The areas of the strongest fields coincide exactly with the position of sunspots. Here, the magnetic field strength can be amplified 10,000 times.
It turns out that the regions of the strongest magnetic field on the sun are in sunspots, and in the units that we use, sunspot magnetic fields are roughly 1,000, 2,000, maybe 3,000 Gauss. But if you look at magnets like the ones I'm playing with here, the magnetic field in these magnets is about 1,000 to 1,500 Gauss. So these have roughly the same magnetic field strength as a sunspot. The key difference, of course, is that a sunspot is an awful lot bigger, and so the total energy, or the amount of energy in the magnetic field on the sun, is enormous. But the field strength at any given location is something you can hold in your hand.
Sunspots are just the visible effect of magnetic fields so strong that they can prevent the heat and light rising from the sun's interior. With the right viewing equipment, you can even see the magnetic fields. Magnetic loops arch off the surface. Like iron filings around a bar magnet, their shapes are mapped out by plasma heated to 1 million degrees. The largest are 200,000 kilometers high, and they are packed full of unstable energy.
When you add up the total energy content in these loops, it comes out to roughly 10 to the 21 joules of energy, and that's roughly 10 times the annual energy consumption of the United States. Of course, we can see thousands of them at any one time.
The loops are caused by the twisting of the sun's basic magnetic field. Because the sun rotates faster at the equator than at the poles, it drags the field lines with it, stretching and twisting them like elastic bands. As the solar cycle goes on, the fields get more and more twisted and break through the surface. Until at solar max, the whole sun is covered in loops, stretched to breaking point. Solar flares are what happen when the strain gets too much and the loops snap.
Basically, all that energy comes out of the catastrophic release of energy that's been stored in the magnetic field. So, like if you wind up an elastic band too much, if you let it go with your fingers, that elastic band flies across the room.
When the energy bound within sunspots is released, billions of tons of plasma are fired far into space at huge speeds. And sometimes they are aimed straight for the Earth. The flares fly through space for 2 days. When they reach us, the Earth's own magnetic field deflects most of the blow. But it is the impact on the magnetic field which affects the Earth. It's called space weather, and the best of its effects are magical. The auroras, dancing displays of celestial light, are caused by particles from the solar storm smashing through the magnetic field at the poles. When they strike the upper atmosphere, they light up the polar skies. In the strongest storms at the peak of the solar cycle, the northern lights can be seen as far south as Athens and Cuba. But the buffeting of the magnetic field has other unseen effects. Migratory animals that navigate using the magnetic field can lose their bearings. Racing pigeons don't come home. And whale strandings have been seen to increase with solar activity. But most worryingly for us is the effect that the disrupted magnetic field can have on electronics. The strongest storms can damage or destroy satellites with devastating effects.
We're sort of more sensitive to the sun than we probably realize, because when the sun releases this magnetic energy in the form of solar flares and coronal mass ejections, maybe you don't notice it at first, but a little crackle on your cell phone or your cell phone going out may actually be caused by enhanced activity on the sun.
Mobile telephones, television, aeroplane navigation, even weapons guidance systems all rely on satellite communication, and all can be disturbed by space weather. The more we are reliant on these systems, the more we will feel the effects of the sun's tantrums. But we still don't understand all of the effects of space weather. No one can explain the effect on the climate, or why the disappearance of sunspots should cause an ice age. It may not matter. The small effect that solar variation has on the climate has long since been drowned out by man-made global warming. As the world warms up, the sun may yet prove an unlikely source of cooling. The greenhouse effect could be stopped by harnessing its heat. The American Indians of the Southwest deserts have understood the importance of living sustainably with their environment for hundreds of years.
We have the natural disasters, like the big old fires, the volcanoes erupting, the big old earthquakes, the tsunami. That's the Earth telling us that it's getting pretty tired. It's warning us that we need to slow down.
On the mesas of Arizona, far beyond the reach of the electricity grid, lies Old Oribe, the oldest occupied settlement in North America. For 1,000 years, the Hopi Indians have lived here in harmony with their environment.
Archie seems to rather...
But that doesn't mean that they have to live without the conveniences of modern life. They have just realized that they are already getting all the power they need. Under the clear skies of the desert, a family can be supplied with electricity from a couple of solar panels.
Being that we pray to the sun every day, it's got our heartfelt desires. He receives it every day. We thought the best source of energy should come from the sun.
A few miles across the desert, the idea is finally catching on with the rest of American civilization. But naturally, it's on a much bigger scale. These are Stirling dishes, the daddy of solar power systems. And they may be about to solve the energy crisis facing the cities of the American West.
People want to run their air conditioners, their computers, their lights during the day, and we run out of energy. We have a solar furnace 90 million miles away that provides life for all of Earth. In the past, we've been unable to harness that potential because the efficiency, the cost, et cetera, of the system just didn't make it viable. What's changed is technology. The technology now allows us to build large-scale, highly efficient, cost-effective systems.
Each dish tracks the movement of the sun across the sky, focusing the heat onto a single point, where it is converted to electricity. They are twice as efficient as any other solar power system. With one, you could power a small village. A field of them could power a city.
Each system produces about 25 kilowatts, which is enough to power about 10 homes. However, we plan to deploy these on a large scale, 20,000 of these, which is massive, about 500 megawatts, which is the equivalent to a coal-fired plant or maybe even a nuclear plant.
The ink is just drying on the contract to build the first commercial solar power station. It will fill 5 square miles of the vast Californian desert with mirrors and will supply electricity to the city of San Diego. In time, as the technology and efficiency improves, systems like these may spread around the world. These dishes are direct descendants of the stone monuments of Stonehenge and Orkney. Separated by 5,000 years, they all embody our desire to understand the sun, to be bathed in its light, and to tap into its awesome power.
He's quiet, he's clean, he's powerful. This is the way I was raised. I was raised to respect him and to offer those prayers to him for keeping us for the length of time that he has. You know, he's done this for generations and generations, and hopefully he will, you know, in the future.
The sun will probably shine down on our civilizations for as long as they exist. If we survive for another billion years, the sun will still be there. But just as the sun was once born, it will one day die. And when it does so, it will take the Earth with it. In about 5 billion years' time, the sun will run out of hydrogen. When it does, it will become a red giant. Deprived of fuel, the core will shrink, generating so much heat that the outer layers will balloon into the solar system. The inner planets will be swept up. It may even swallow the Earth. Whether it is engulfed or not, the Earth is doomed. The sun, burning 2,000 times hotter than it does now, will melt and seal the outer layers of the planet. Then suddenly, the sun will stop burning. As the remains of the solar system is plunged into darkness, the sun's core will collapse, and with its last gasp, it will blow its remaining shroud of gas into space. It will be forever night. The story of the sun and the Earth will have ended, and a small part of the outer arm of the Milky Way will be a little bit darker. But around it, in the rest of the universe, the same story will be being told by a billion other small, insignificant stars twinkling in the vastness of space.